This chapter introduces the fundamental principles of semiconductors, focusing on the material's properties, electrical behavior, and role in electronic device construction. It sets the groundwork for understanding advanced topics like diodes and transistors, which are detailed in later chapters. Key topics. 1. Properties of semiconductors. Semiconductors, like silicon, have conductivity between conductors and insulators. Silicon's crystal lattice, composed of covalent bonds, is detailed, with conductivity affected by temperature. 2. Doping. Doping introduces impurities, atoms with different valences, to pure silicon to increase charge carrier concentrations. N-type silicon dopants like phosphorus add free electrons. A P-type silicon dopants like boron create holes, positive charge carriers. 3. Current mechanisms. Drift. Current. Charge carriers move under an electric field, with velocity proportional to the field strength. A diffusion. Current. Carriers move from regions of high to low concentration, forming gradients. 4. PN junctions. A PN junction combines P-type and N-type silicon, forming a depletion region where charge carriers are depleted. This structure underpins diodes and transistors. Behavior under forward and reverse bias is explored. Forward bias lowers the potential barrier, increasing carrier flow. Reverse bias heightens the barrier, limiting current to a minimal leakage. 5. Capacitance in PN junctions. Depletion. Capacitance arises from the charge stored in the depletion region. The junction's capacitance varies non-linearly with applied reverse voltage. 6. Breakdown phenomena. Zener. Breakdown occurs at low reverse voltages due to a strong electric field breaking covalent bonds. Avalanche. Breakdown. At higher voltages, carrier collisions cause ionization, increasing current rapidly. Real-life examples. Semiconductors in electronics. Silicon's dominance in microelectronics, including processors and memory chips, illustrates its role in modern devices. End example. Smartphones and laptops rely on silicon-based transistors for their operation. 2. Doping for improved performance. Tailoring doping levels in LED materials enhances brightness and efficiency. 3. PN junctions in everyday electronics. Diodes in chargers ensure unidirectional current flow, preventing damage from reverse polarity. And solar panels utilize PN junctions to convert sunlight into electricity. 4. Breakdown mechanisms in voltage regulation. Zener diodes in power supplies maintain constant output voltage, protecting sensitive circuits. Summary. This chapter builds a foundation for understanding the physics of semiconductors, essential for studying electronic devices. It explains how semiconductors' properties and controlled modifications through doping enable current flow and device functionality. The PN junction's critical role in devices like diodes and transistors highlights its importance in electronics. Real-world applications of these principles underscore their practical significance.